guys, here it is, the last lecture. We're going to be talking about solutions. And we've looked at solutions and used solutions when we were doing small scale chemistry when we were still at school. But we need to kind of think about what's actually going on in there in a little more detail than what we've done in the past. So to do that, we're going to start by thinking about a really simple, familiar solution, and that is Kool-Aid. So you take some water, have your Kool-Aid pouch flavoring, a cup of sugar, and you mix it all together, and you have Kool-Aid. So you end up with a color change, and the solid sugar dissolves and disappears. And so considering this really simple solution, we want to think about some of the basic vocabulary for solution chemistry. Solution, solute, and solvent. So the solution is the final product. So this red Kool-Aid over on the right, that is the solution. The solute is what gets dissolved. So the Kool-Aid pouch and the sugar, that's the solute. And then last, we have the solvent, which in this case is water. And it's often water in many cases, especially in this class. So if we want a formal definition, the solution is a homogeneous mixture, homo meaning the same, so you can't tell it apart. It looks like it's just one substance, like one liquid, but it actually consists of a solute and a solvent. The solvent is the dissolving substance in a solution, so that's sugar in our Kool-Aid example. Lastly, we have the solute. Oh, sorry, I said that totally wrong. The solvent is the water in the Kool-Aid example, and the solute is the sugar, so the particles that dissolve in the solvent to form the solution. So solvent is the water, solute is the sugar. Here's another example of a solution that we can consider. This time we have a pitcher of water, we have a chunk of granite rock, and we have a cup of sugar. We're going to mix the rock and the sugar into the water. And as you can see with my really, really top-notch Photoshop skills, the rock just sits at the bottom of the pitcher and it does not dissolve or disappear, which is unlike the sugar because the sugar does disappear into the water. So we want to think about what the difference is in that case. We also want to think about, if you keep adding sugar, is it going to continue to dissolve and, kind of disappear forever? And if not, what do you think is going to happen? So, you can do this experiment in your kitchen, or take my word for it. If you keep adding sugar into the water, eventually the sugar will stop dissolving. And at that point, we say that it's a saturated solution. And so then after that, you just have sugar piling up on the bottom of your glass of water or pitcher of water or whatever you have. So for talking about solutions, we have solubility, which is the amount of a solute, so the amount of sugar that dissolves into a given quantity of solvent under specific conditions, like the specific temperature and pressure, to create a saturated solution. So if you're dissolving sugar until it stops dissolving, that is a saturated solution. We know that if you heat up a solution, so if you heat up, a hot cup of tea, it's easier to dissolve stuff than it is in a cold solution. And so that's where temperature comes into play. The saturated solution contains the maximum amount of solute. If you add more solute, it does not matter because it's not going to dissolve. Okay, so there's a couple different types of solutions. And one of them, which is primarily what we've dealt with, is aqueous solutions. For example, sodium chloride, which is salt, plus liquid water, is going to dissolve to become aqueous sodium chloride, which really just means the sodium ion is by itself interacting with the water molecules, and the chlorine ion is by itself interacting with the water molecules. And if you dig way back to ESS, if you took ESS with me, we talked about how the polar water molecule, right, the negative polar side of the water, which is the oxygen, is going to be attracted to the positive sodium, and the slightly positive side of the water molecule is going to be attracted to the negative chlorine. Another example is sugar. So this is just a simple glucose molecule, C6H12O6 plus H2O liquid gives us aqueous sugar. So now we want to think about, what's different about these two things. So what kind of compound is being dissolved in each example, and how do they behave differently when they are dissolved by the water? So we're going to look for some similarities, and we're going to look for some differences. Oops. If we consider these, they start out really similar. They're both solid, and from our prior knowledge, they're both kind of colorless, opaque crystalline structures, and we know what liquid water looks like. If we dissolve salt or you dissolve sugar in water, it's clear and colorless, and then this is not something we can see on a macroscopic level, but on a microscopic level, we know that the sodium and the chlorine break apart. So that's an ionic bond, and so it's breaking back into its ions because interacting with the water is a lot more appealing than interacting with the other ions. And the water is really attracted to the ions, so it kind of bullies its way in there. The sugar, on the other hand, is covalent, and so it does not break apart. It stays together. And it's a polar molecule, and that's what allows it to dissolve, but it doesn't break apart because it has those strong covalent bonds with the shared electrons, and so it stays together in one piece. Acids are another common type of solution. We worked a lot with HCl. We worked with so hydrochloric acid, sulfuric acid, phosphoric acid in our labs. And so if you have HCl, which naturally occurring HCl is actually a gas, and then we dissolve it in water, and that produces a hydrogen ion that's aqueous in solution and a chlorine ion that's aqueous in solution. If we look at bases, then we have sodium hydroxide, for example, which is a solid, plus liquid water, and that also breaks apart into a sodium 1+ ion and a hydroxide 1- ion. Looking at both of these are ionic compounds, or they're acting like ionic compounds. And so because of that, we can see that they split up when they're dissolved in the water. So they're similar because they dissolve and become aqueous in solution. They have a cation and an anion. But they're a little bit different because they have different types of cations and anions. So The acid is unique because it has the H plus, that's what makes it an acid. The base is unique because it has OH minus, that's what makes it a base. So aqueous solution is a solution with water as the solvent. So we've got our sodium chloride and water example, and we've got our sugar and water example. An acid is a compound that produces hydrogen ions when you dissolve it in water. So hydrochloric acid plus water breaks the hydrogen out. Bases produce hydroxide ions in solution. So anything that has an OH minus or an OH as an ion, that's going to be acting as a base. And something that we're not going to have a chance to really get into, which is a shame because it is my favorite lab of the whole year, is neutralizing acids and bases. If you have an H and you add an OH, you have H2O. So if you mix an acid and a base in the right amount, you're going to actually just make water. And there's not going to be any acid or any base anymore. And so that when we do that, it can be called titration. And it's a really fun lab because you're trying to make them perfectly equal. Very frustrating at times, but super fun, and it has pretty colors. So it's a bummer, y'all, that we don't get to do that together. Anyway, back to our Kool-Aid example. So how could we describe how much solvent is in the solution and how much solution we have? Also, how could we describe how much solute is in the solution? So for solvent, we're talking about liquid water, so we could measure it, we could measure in cups. You could say I have 8 cups of water. You could say I have a liter, I have a gallon. Those are all familiar ways that we could measure it. And then if we want to talk about the solute, right, we already have a unit given for the sugar. We have a cup of sugar, but we could measure it in grams. We could measure it in kilograms, we could measure it in pounds, and all those different tablespoons, right? And so we would quantify it in those ways. Now, if we're talking about chemistry, typically we're going to use SI units. And so we're probably going to be dealing with liters for our solvent and probably grams or kilograms for our solute. And so those are the 2 ways that we're going to really measure how much of this stuff we have. So instead of constantly listing off how much solvent and how much solute, we have some units of measurement that are specific to solutions that we can use instead. The most important and the most common is called molarity. Molarity is the concentration of solute in a solution expressed as moles of solute dissolved in 1 liter of solution. And so it looks pretty similar to this other one called molality. Molality is less common, but can come in handy if you only have a balance to work with. So molality says the concentration of a solute in a solution expressed as moles of solute, so that part's the same, dissolved in a kilogram of solvent. So there's a big distinction here, a liter of solution. So that's how much stuff there is with the solute dissolved in it. But a kilogram of solvent means you would measure the mass of the solvent before you add the moles of solute. So in molarity, you're going to add your moles of solute, and then you're going to fill your container to 1 liter to have a liter of solution. In molality, you get a kilogram of solvent, and then you add your solute afterwards. So it's a little bit different. The equation for molarity, capital M, is moles of solute divided by liters of solution. And molality is a lowercase kind of cursive m, and it's moles of solute over kilograms of solvent. We are going to practice using these in the next part.